Hi, welcome to another edition of Linear Algebra. Today we are going to continue our conversation about matrix operations and in particular multiplication. So let's go and take a look at this technical topic. We are going to have a list of small topics to go through. Let me just remind you what we did last lecture and we take it from there. So we said our long-term plan is to duplicate everything we did from elementary school through calculus, but do it all for matrices. So that's our big plan. And at the end we are going to connect that to the idea of vibrations. So we talked about addition and subtraction and linear combination. There wasn't anything surprising there. We talked about multiplication last time, and our plan is to talk about division and powers and functions later on. So addition and subtraction were straightforward. Multiplication we did last time. We explained that the case of multiplication is essentially a long list of dot products. So for example, if I have this matrix with yellow rows and this other matrix which is a case of blue columns, to multiply these two matrices, it means to multiply each of the rows of the first with each of the column of the second and record the result in corresponding location. So for example, 362 had to be multiplied with 173 as dot product of two vectors. The result was 51, and we just wrote it in first row or first column, and then we have to keep doing that. So let me say that we need to practice the idea of multiplication so that we are comfortable when it comes up in a variety of special circumstances. We'll be able to handle it quickly and move on. So as of this point, we had the long list of dot products. For the dot product to work, the length of this row vector and the length of this column vector had to be the same. So that meant the number of columns of the first and rows of the second had to be the same for multiplication to work. So that was our compatibility. Now let's take a look at some special cases. So what I have here for you for today, special cases of matrix multiplication. First, because we actually need them, and second, as extra practice on multiplication. So these are going to be matrices of special look. For example, just a row times a matrix, or just a matrix just times a column, or a row times a column, or a column times a row, or a diagonal matrix times an arbitrary matrix, or a matrix times a diagonal matrix, and so on. So we have a long list of these little practice points that we are going to go through, and then we are going to mention a set of ideas that are going to be in connection to this. So let's go after item number 1. So what happens when I have a row and I want to multiply it by matrix? Best thing to do is just to practice a simple case. So suppose I have a row such as let's keep it simple, 1 2 3, that's a row. I have to multiply it by matrix, so I'll say 4 5 6 and then 7 8 9. Okay, so this is my first matrix is just a row, and the second one is just something arbitrary. Nothing any different from what we had done before. We take a row, here and multiply as in doing a dot with each of the columns of the second. So that is all we are going to do. Nothing any different. It's just getting used to idea that our matrices could be of a special size such as just having one row. So 1 times 4, so it's going to be a 4, and then 2 times 5 is a 10, and 3 times 6 is a 18. So I have a total of 32 as a product of my row and the first column. So 32 is the first entry. Then I multiply yellow with a blue second blue column. So I'll have 7, and then 16, and then I'll have 27. So so I guess that's a 50. Well, what if I want to multiply a matrix with a column vector? So suppose I take the same thing, 4, 5, 6, 7, 8, 9. Suppose I want to multiply by a column vector. What should be the size of this so that we can actually do the job? So again, remember, we are taking rows of the first, multiplying by the columns of the second. And this multiplication is just a dot product. So here I have to have exactly two items, like just 1 and 2, because that's to match this yellow row on the left. Then 4, 7 times 1, 2. So what's that going to be? So 4 times 1, so there's going to be a 4. 7 times 2, it's going to be 14. And then we have to add them, so first entry becomes 18. Then 5, 8. So each of these rows has to be multiplied. So 5, 8 is going to be 5 and 16. So it's going to be 21. Second entry 21. 6, 9 times 1, 2. 6 times 1 is a 6. 9 times 2 is an 18. And then I'm going to make it 24 out of it. So you're going to see most multiplication looking like the second one, but the first one might show up as well. Let me put the rest of them further down so that we have more room. A row times a column. What happens? We have, so a row, if I have a row column, and then I want to multiply, so a row vector times a column vector, such as what? So like 1, 2, 3, and a column vector like 4, 5, 6. Remember the way we are doing all of these things: a row of the first and a column of the second. While we have one of each anyway, and when you are doing a dot of these two, so it's going to be 1 times 4, 2 times 5, and 3 times 6, and whatever that is. So 4 and 10 and 18. Out comes a very special matrix. It's just size 1 by 1. There's just one number in it. For all practical purposes, that's just like number 32. So a row times a column is straightforward. A little bit more confusing is the case of column times a row. Like if I had my column here 4, 5, 6, and the row 1, 2, 3, what is that going to be? This special situation has a name for itself. It's called outer product. Fancy name. And now let me also tell you, aside from being fancy, it's something that you actually did in elementary school. In what sense? Well, let's see. 4, 5, 6. Each of these rows has just one item in it. And then 1, 2, 3. Then we have 3 columns. So when you want to multiply, what are you supposed to do? A yellow and a blue. Each of them are kind of very short items. 4 times 1, that's it. There's nothing else to do. 4 times 2, 4 times 3, 5 times 1, 5 times 2, 5 times 3, 6 times 1, 6 times 2, 6 times 3. Well, what does this look like? I was telling you, it's just exactly what you did in elementary school. Over there, they would be writing a multiplication table for you, and there would be some numbers, perhaps starting from 1, going as far as 10, and sometimes peculiarly they go to 12, as if doing more of it, you get more or something. Anyway, and then here you have 1, 2, 3, and perhaps you go as far as 9 or whatever you might have. So you just put your numbers on the margins of the table, and then you multiply each number on the left with each of these numbers on the top here, and so you get 4, 8, you say 4 times 3 is 12, and so on, 5, 10, 15, 6, 12, 18. So it's just that it's not written in this style. So in this one we had the items that are multiplying sitting on the margins, and then body of the table is the result of multiplication. But what we are doing right now, we are just writing into this style, and the result of multiplication is dragged to the right, and then we're doing it like that. So that's called an outer product, as opposed to what we had an inner product, you remember, and then so the two of them, not to be confused with each other. So we talked about this case, row times column, column times row, called the outer product. Let's go now take a look at special case of a diagonal matrix times a matrix, or a matrix times a diagonal matrix. You remember, diagonal matrix itself was a matrix that had some entries on the diagonal, and everything off diagonal was 0. So if I have A, B, C, and then 0, 0, 0, 0, 0, 0, anything above or below the diagonal being 0, that is called the diagonal matrix. So diagonal matrices are our friends. If that's all you have to deal with, that's kind of like your lucky day. It's as close as you can get it to being just ordinary calculus. Now, what if I have one such matrix and the other one is just an arbitrary matrix? Arbitrary means anything can show up anywhere. So let's go ahead and talk about this one. A diagonal matrix times an arbitrary matrix. So maybe let me write it out. It's a diagonal matrix then times an arbitrary matrix. Let's go ahead and practice some parametric cases. Let's keep it short to A, B. And this one, arbitrary matrix, let me call it X, Y, and Z, and T. Okay, so diagonal meant we have some entries on the diagonal. Off diagonal there are 0. Arbitrary means anything goes. Well, how are we supposed to multiply? Not any different than what we have been doing over and over again. So let's go ahead and do this. So what happens here? Yellow times a row times how times as a dot product. So let me write it all out. AX. Next item is 0 times Z. Well, that is of course 0. The first yellow with the second blue, so that's going to be AY plus 0T. Again, that's just 0. Second yellow with the first blue, so it's going to be 0X plus BZ. So that portion goes away. Second yellow, second blue, so it's going to be 0Y BT, and again this one goes away. So when you clean it all up, what's left? AX, AY, BZ, BT. Okay, you might be wondering, well, so what? Let's do it the other way. Meaning what? Meaning arbitrary is first, diagonal is on the right. Okay, so meaning what? X, Y, Z, T is on the left, A, B is on the right. How do we multiply? Again, rows of the first with the columns of the second. Let's go patiently write that. XA, and then what? Y times 0. So Y times 0, of course that's just 0. So first yellow, second blue. So X 0, Y B. So this portion is just 0. And then ZA plus T 0. Of course that is 0. And then what? Z times 0 plus T times B, so that is 0. What when we clean it up and write it just like a civilized person without having all those useless zeros? Okay, what do we learn from here? Several things. One big surprise is that it matters who's on the left, who's on the right. Like this is not the same as that. Look here, I have a BZ here, I have ZA here. These are different. AY here, YB here. On the diagonals are the same, but off diagonals are different. So one thing we learned, and we are going to talk about it extensively later on, is that the order of matrices that show up in your multiplication are going to make all the difference. Item number 2, where we are learning about special case of multiplication. Here, special meaning the first one is diagonal. How do we remember that? It is as if you multiply the first entry of this diagonal with all of this row and second entry with all of the second row. Is that same way here? Well, look at it. Take for a second and let me see if we can discover a little rule that tells us. So here's your clue to think and come up with an answer. How would you verbally describe how did this multiplication work out? So if diagonal is on the right, what's happening? Each diagonal entry multiplies an entire column, AX and AZ, or ZXX, ZA, as opposed to here that each diagonal entry multiplies an entire row. So when you're on the left, when diagonal is on the left, you're influencing the rows by rows. When the diagonal is on the right, you're influencing column by column. Okay, so that's another practice we had for today. So that takes care of this. We already had a preview of this peculiar situation that we have is going to be plaguing us from now to the end of time, to the end of linear algebra. We have lost commutativity. If you have two matrices, chances are when you want to multiply them, perhaps A times B is defined and maybe B times A is not defined. Even if both of them are defined, there is no guarantee that they'll be the same matrix. We just saw an example. So a matrix times another matrix, then I reverse the order. The results are different. You can pick any two matrix, say two matrices, to keep it simple, square of same size. When you multiply them, it is very unlikely, well, sometimes it might happen, very unlikely that the result will be the same. So one thing that has happened here is the fact that AB is no longer same as BA. You might be wondering, well, they have been telling me for 13 years so far, from kindergarten to all the way through calculus, that multiplication is commutative. Everybody has been telling me all along that x times y is y times x. Why is that so? Were they lying to me before, or are you lying to me now? What's going on? Well, very simple. We are using this word. Okay, we are using the word multiplication. It has to be taken with a grain of salt. This is matrix multiplication. We notice that it's quite a complicated operation. It's built on top of what you had done in high school, but there's a lot more added to it. So there is no reason for us to expect that it will be having the same properties it had before. Well, some of the properties that we seen before, we are going to see that they're still there. So there is some cause for calling it multiplication, but perhaps we could have invented some other word there so that it will stand out as a flag that, okay, this is a different deal. Do not get it confused about that. So let's go ahead and emphasize that we have no commutativity. A times B in general, In some special cases, it might happen that A times B is B times A, but you cannot assume it. So that we write it as loss of commutativity. Well, is that the only thing that's lost? Well, any idea you had in ordinary algebra where this commutativity was used there is going to be in jeopardy now. For example, what do you think is A plus B squared? Say A and B are two matrices, and squaring means just multiply by itself. Let's just remind ourselves that in high school, if you have a number added to another number and you want to square it, we have this identity that we use it over and over again. Square of the sum, square of the first, square of the second, and twice the first times the second. Is that the same? Well, let's just go ahead and see. Well, first of all, what does squaring mean? Squaring means multiply by itself. And then first times first, first times second, second times first, second times second. Well, we have the shorthand that something multiplied by itself, we write it as a square. So this is A squared, this is B squared. The fight is over what to do with here. Due to the fact that AB is not same as BA, I cannot write this thing. This is not same as 2AB. It's not same as 2BA either. There isn't anything I can do with this in general. I just have to leave it alone. So the squaring identity in linear algebra for two entries that are matrices, square matrices, is going to be like this. Not as interesting as it was in ordinary algebra. You had in algebra 1, 2, pre-calculus, calculus 1, and so on. It always worked like that. That we have lost that. Let me see if you can see what's going on. Let's do another one of the identities we have. Might suspect something's going to happen based on what we have talked about in comparison with what happened in high school. In high school, if you have sum of two numbers times the difference of these two numbers, what happens? Well, what happens is that you have x squared minus xy plus yx minus y squared. And then you have the cancellation and you get x squared minus y squared. The question is, can I write the same thing here? Is this same as a squared minus y squared minus b squared? Well, let me see. Take a second or maybe 30 seconds and tell me, well, does this thing sound true to you? Of course, you get the idea that this can't be that. And that's not the factorization of this thing either. Why is that the case? Because a times a will be a squared. That's fine. Then you have minus ab, and then you have ba, and then you have minus b squared. The problem is that these two do not cancel. These two do not cancel each other because they're not equal to each other to begin with. So the sum is not zero. Here it was, but now we have lost that. So this thing shows its head a variety of places. You cannot discount it. If you consider it a good thing or bad thing, that's depends on your point of view. But we just have we had one casualty of this definition is that we have lost commutativity. Well, certain things are not lost. If we had lost all of those properties we are used to in high school, we wouldn't be so interested in this thing. But let's go to something where at least some of the ideas we are used to are still there. Let's go to the concept of a power of a matrix. So power of a matrix, in high school you start with a variable and then various powers of that variable. These are building blocks of all sorts of algebra you do. So for example, what do you mean by x cubed? Well, you mean that number multiplied by itself 3 times. So the concept here is, if I have a matrix, I want to go ahead, see what's a squared, what's a cubed, what's a to the power of 4, and so on. If you notice for a second, the only way you can define this thing is for a to be square. A must be square for you to contemplate its power. Like if I have a rectangle like 1 2 3 4 5 6, if I want to square it, meaning I multiply it by itself, well, this is not going to work. It's not going to work because the number of elements in this row and in this column don't match each other, so I'm stuck. I cannot multiply. How am I going to dot with something with 3 elements with somebody that has 2 elements? That doesn't work. So a must be square. That's a requirement. Okay, suppose we start with a square. Then a squared, no problem there. How do you define it? Just as in ordinary algebra, the thing times itself. How about a cubed? How do you define that? Well, you say, well, just like that. But you have to have a way of doing things one at a time. One at a time means either you multiply these two first and then you go after that, or you multiply these two first and then you go after that. Meaning you have 2 options to do here. One is a times a squared, and the other one is a squared times a. If you are paying attention, you say, well, you just told me the matrix multiplication is not commutative, so I have to watch out that this is different from that. But it so happens for the powers of a matrix, that's one of those nice situations where we actually still do have commutativity. That is, if you take a and multiply by a squared, or you take a squared and multiply by a, you actually get the same answer. So it is legitimate to write a cubed, write it this way, this way, this way. These are all the same. Now I invite you to try to see how many different ways you can multiply a's to make a4. That's actually a problem in a field of mathematics called discrete mathematics, where you do a counting of how many different ways can I do something. Well, what do you mean? Well, I can do, for example, a and a cubed. Is that right? What else can I do? Well, of course, I could have done a cubed with an a. That's another legitimate way. And then you can think about other ways. What else is left? Can you think of something else? Again, let me encourage you to think what other ways can we define a4 as. Well, of course, you could have at a squared times another a squared. And then gradually a question comes up, if you have all these different ways of doing it, what's the smart way of doing it? So I'm going to leave that out. If you do take a course in CS and such, that's probably going to be one of the basic questions there. The nice way of describing a big idea that we have here is that if you have a power and then some other power of the same matrix, same square matrix, you can write it as a to the power of n plus m. So that's exactly the same rule that you had since Algebra 1. They probably write it like this in your Algebra 1 book, that if you have same base, different powers, you add up the powers and such. Same thing applicable here, at least for all positive integers here. Okay, that is a little bit about power. So for powers, we do have commutativity, and we do have this rule that's identical to the rules from Algebra 1, Algebra 2, and so on. Okay, next question is, okay, these are all sound nice. First of all, you didn't prove that this is true. Yes, we are just mentioning and moving on. Second thing, matrix multiplication was so expensive, so lengthy in operation. So is this really a practical thing, or just something nice to look at? Practical meaning, if I had to find the 100th power of a matrix, am I going to be doing this type of matrix multiplication that we have been doing all along? This type of matrix multiplication, is this can somebody actually sit down and do this 100 times? Well, as I said, we are using this thing because it's a powerful way of solving certain problems, and we had advertised that we want to do entire calculus for matrices. And of course, in calculus, especially in calculus 2, you have this so-called Taylor series and the powers of your variable and such, and of course we need to be able to duplicate that in an efficient way. To learn how to do it efficiently, we have to go all the way to the end of this semester to see how to handle power, special case of multiplication, that's power. How do you do it? We still have to wait, but we can do some special cases now, and you are going to see some of these things in your exercises. So for example, here might be a simple exercise. Suppose, so for some matrices we can handle the situation. Suppose I have a friendly matrix. Here's a very friendly matrix. Everything is 1. And the question is, find a to power of 100. Of course, if this problem was something that you had to sit down and do something 100 times, and each of those steps was some painful steps to go through, of course you wouldn't do it. So there must be some way of doing this thing that is not a painful exercise. So how do we handle this type of problems? We just don't get scared by big numbers and such. We make the problem simple for ourselves and go step by step, see what we can find. So the way to go after this is to detect a pattern. That is, we write a, then we write a squared, then we write a cubed, and see if we can see the light at the end of the tunnel. The sooner that we see this thing, the faster we are going to go to 100. And the whole thing leads to approaching mathematics that you might have seen some places, but we are not going to spend time on it. Some style of approaching mathematics called induction method. Induction method is kind of like a case of dominoes that one falls on the next and the next and the next. Something like that happens in mathematics too, and if you discover something like that is going on, you can predict how those dominoes are going to fall. So what we do here is, okay, a is fine, it's just 1 1 1 1. How about a squared? Well, that's supposed to be 1 1 1 1 times itself. Well, this is not painful, I can do that. 1 1 times 1 1 becomes 2, and this is 2, and this is 2, and this is 2. So that wasn't that bad. Now you can factor the 2 outside, or you can just leave it like that and come after a3. a3, we said, simply means multiply this item 3 times. Well, you can decide to do these two first, but good, luckily you have already done it, so we can just borrow that, and then you have to multiply by another one. So what happens? Well, just patiently do what we have been advertising all along. What happens if I multiply a row and a column? Of course I get 2 plus 2, which is a 4. And the nice thing about this simple matrix is that everywhere same thing happens. Again, a good thing would be just to factor 4 out and have even a faster way of doing it. But if you don't think about it doing that way, that's fine. So what happens into a4? a4, I can think about it as a3 times a, and a3 was 4 4 4 4, and a was 1 1 1 1. And then of course when I multiply a row and a column, I get 8 8 8 8. Well, feel free to press on the buzzer as soon as you see the light at the end of a tunnel. What is happening? So can you tell me right off the bat what A5 is going to be? And does everybody see that it's going to be 16, 16, 16, 16, and so on? So what's going to be a to the power of 100 then? Well, so when I have power 2, I have 2 to the power of 1. So this is made out of 2 to the power of 1. This is 2 to the power of 2. This is 2 to the power of 3. This is 2 to the power of 4. Always one less than the power I needed over there. So this stands to reason that it's going to be 2 to the power of 99. And with these problems, you don't want to crank up your calculator and find out what 2 to the power of 99 is. That's not the point. The point is to discover the pattern, not the something that the computer is going to spit out at you. Okay, so that's the answer, and that was a simple example. A couple of examples like this you're going to see in the textbook, where you're going to detect a pattern. Sometimes the pattern might take a while to show up, and it might be a bit more involved, but in general it's possible. So notice we didn't suffer through like 100 cases of multiplication, and later on we are going to have any matrix, nothing special about the numbers, nothing friendly or such. We can handle those too, but it takes about a month of preparation for us to harvest that intelligent approach and be able to do this thing. So once again, we need also the powers because we want to duplicate the entire calculus, and then right now easy ones can be done like this, and later on more complicated one we have to wait until the end of the semester. Every now and then your homework might ask for some general power. Once you see the pattern, you can just write down the applicable formula. Now in mathematics, again, they go and make this approach a bit more solid than what I made it out to be, and make a whole case out of it called Induction Method. I invite you to read about it, but we are going to move on. So we lost commutativity, but we still had some familiar grounds like high school with the case of powers and such. Next up, we are going to inject something into discussion that you never had in calculus, and that's the idea of a transpose. Transpose, well, everybody works with a phone. Sometimes you hold it up, sometimes you hold it sideways and such. A matrix can be handled the same way. You can just turn it 90 degrees and make another matrix out of it. We already talked about the rows versus columns and such, and sometimes you want to take a matrix and flip it around. So that is what the case of transpose is going to be. So we have idea of a transpose of a matrix. So if you have a matrix A, the transpose of it might be written as A with a T on top of it. Sometimes like people like to put a apostrophe around it, or some other decoration to indicate a transpose. What's the idea? Suppose A is 1, 2, 3, 4, 5, 6. A transpose is going to be a matrix that is made out of turning the rows of this thing into a column, and the columns of it into rows. So row 1 became column 1, row 2 became column 2, or you can say column 1 became row 1, column 2 became row 2, column 3 became row 3, and so on. So that's the idea of a transpose of a matrix. Of course, you would not see this thing before because all along you have been dealing with just one number. So if you had, say, number 5, when you transpose it, it's still 5. There's nothing to be gained by taking a one-by-one matrix and transposing it. So you didn't ever see such a thing in any calculus book. But now we have to inject it inside the list of our primary operation and say, okay, transpose is something for us to include in the list. It's not as much of a major thing as the rest of the stuff we are going to do here. It's kind of on the side, but it is necessary as a little operation that we are going to carry around. So let's go back and say a few words about transpose of a matrix. Okay, so here's a transpose. Let me take another one. Let's suppose I have a matrix B and I write a special matrix here, for example 2 3 5 and then 3 9 and say 11 and then 5 and 11 and say 23. Now go ahead and find for me what the transpose of this matrix is going to be. Convert the rows to the columns and columns to the rows. So let's take this rows and then I'm going to plant them in these columns. So I'm going to put that that 2 3 5 that was here. Here's my 2 3 5. So I took this and I put it down like this. Second one 3 9 11. And third one is 5 11 23. Well, I spent all that energy and ended up exactly where I was. So sometimes a little bit unsettling and looks peculiar. In mathematics, whenever you do something and at the end it looks as if you have done nothing, you say you have symmetry. Like for example, if you take a circle and turn it, you still have the old circle. Even though you turned it, it's no different than what it was. Then you say this circle has symmetry with respect to this and that. Same here. If a matrix is such that when you transpose it, it looks exactly the way it was at the beginning, then you say their matrix is symmetric. So B is called symmetric. If its transpose same as what it was to begin with. Well, if your matrix is rectangular, obviously this cannot happen because even the sizes don't match, much less for them to be equal. So your square has to be, B has to be square for this thing even to be contemplated. And then what else? What can we tell about when this thing happens? Well, the entries have to look in a certain special way for this thing to happen. Is that right? Like this 3 and this 3 match, and this 5 and that thing 5 over there match. So the entries across the so-called main diagonal have to be the same thing. So for example, what is this? This is item entry of B, which is seated at the location row 2 column 3. How about this one? Well, this is row 3 column 2. So these two have to be the same so that when you exchange them, your matrix doesn't make any difference. So that's not only for 2 and 3, but any one has to be true. For 2 9 23, well, 1 1, when you transpose it, that thing is just sitting where it was. It's not significant what you have on the diagonal. That's never going to have an issue. Is the issue with respect to numbers that are off diagonal. What we expect is that whatever is seated at the location ij has to be exactly the same as whatever was sitting at the location ji for all locations i's and j's, for all the indices, for rows and columns. This must be true. Okay, so on the diagonal this is trivially true. Like if you have b11, it's same as b11 anyway, but what we need is b23 should be same as b32, b12 should be same as b21, and so on. Okay, so that was a little bit about the symmetric matrix. We have something a close relative of this thing called skew symmetric. Skew symmetric, something that comes up in mechanics and such. Let me write an example so that you see immediately what a skew symmetric matrix look like. Suppose I have entry 0, 5, minus 7, and then minus 5, 0, say 11, and then 7, minus 11, and 0 again. Suppose I have this S. It has a peculiar look to itself, is that right? So let's go and write the transpose of it, okay? So just quickly take 3 seconds to write the transpose of this thing for me. What does transpose of it look like? I have to take this row and put it in a column. So 0, 5, minus 7. Second one becomes minus 5, 0, 11. Third one becomes 7, minus 11, 0. Now compare the S and S transpose. What's the relationship between the two of them? What is ST? So each entry of it is a negative of what was over there. You transpose it, it becomes negative of itself. What is causing it? What's causing it is that the items across the diagonal are negative of each other. The only way this happens is that Sij is negative of Sji, and one of the ingredient of this thing is that everybody who's seated on the diagonal, to satisfy this, has to be 0. Otherwise, once you transpose it, it's not going to be negative of itself. So this is the particular case of skew symmetric matrix, and one application of it you're going to see perhaps in your engineering classes. Any arbitrary square matrix can be written as a sum of a symmetric and a skew symmetric matrix. I'm going to write this thing as a problem for you to solve, but we are not going to spend any more time on it. Any square matrix can be written as the sum of a symmetric and a skew symmetric matrix. Very simple idea. I'm just going to give you a little exercise. You're going to do that. Let's just make up some numbers. 5, 7, 11. I must be liking these numbers. 5, 7, 11, 13, 8, 19. What else? 25, 31, 64. Okay, anything. I had a hard time coming up with 9 random numbers, but anything works. What you want to do is to tell me how do you make it out of a, so you want to have a symmetric matrix and a skew symmetric. There are two matrices. One of them looks like this type, and the other one looks like this type. That if you add them, you're going to get your starting matrix there. Okay, so that's a very simple exercise. Let me see if you can handle that, and maybe have a question on this. Then, so we talked about let's see, where were we? We talked about symmetric matrices, we talked about skew symmetric matrices. I'm going to say a couple of words about partitioned matrices. Partition matrices, it oscillates between very trivial and very complicated, and since we are not going to be using those advanced material, I'm going to say a couple of words about what the partition matrices look like. Yeah, well, We have already said a few words about it. Let me one type of partition we saw at the very beginning. If you have a matrix, you can think about it as a bunch of rows, or you can think about it as a bunch of columns. This is one type of a partition. That's another type of a partition. But you could think about many other styles of partitions. So partition simply means creating some blocks in your matrix and then treating it that way. So let me write one matrix, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't matter what numbers you have. Just putting something that's convenient to follow. Okay, this is a matrix. So what is a partition? I can partition like this. Imagine we want to mow a lawn or something, and then you go this way and this way and this way and this way and so on. So that is one type of partition. What's another partition? So we can do this one. That's another partition. So that's another one. And then let's see. Okay. And then is there another partition? Well, yes. For example, I can do partition like this. Meaning, this is this is one matrix I have. This is another matrix I have. This is another matrix I have. This is I'm going to use a different color. Is that right? Okay, that's another matrix. So that's a possibility of one partition. And then again, in order not to write this thing over and over again, can you think about another partition? Well, yes, sure, you can think about another partition. Here's another partition. So you can take a matrix, cut it up into whatever you desire, so long as these lines go all the way. So then you can allocate one matrix for one of these partitions, another one for this one, another for this one, another one for this one. So you can think about a matrix whose entries are submatrices. Okay, so you can stack matrices next to each other so that you make a big matrix. The only thing is, of course, the sizes should match. So we are not going to have any kind of a crooked sitting next to each other. Of course, these two are going to be next to each other if they have same number of columns. A and B can be next to each other if they have same number of rows, and so on. So to be good neighbor, you have to match either same number of rows or same number of columns for things to work. And then you can think about matrix multiplication when elements of your matrix are partitioned. So previously we had talked about compatibility of matrices when you multiply them. Same issue comes up for partitioned matrices. So if you have a matrix that is partitioned as A, B, C, D, and you want to multiply it by another one, let's call it X, Y, Z, T. So imagine that you had 4 blocks here and another 4 blocks here. How do you multiply them? The number of columns of this has to match the number of rows of this one. The number of columns of that one has to match the number of rows of this. And if that's the case, then you can actually carry out your multiplication and such. So partitioned matrices is another topic that comes up in see. So I'm going to let you read about that, and perhaps we are not going to spend that much time on it because it either concentrates on things that are obvious or things that are kind of super complicated. Okay, so we have learned about basics of matrix operations, and now what we are going to do next is put all of the rules that we have together. So we are going to have a kind of a big table of all the rules that we have, and that's going to be the groundwork for everything we are going to do from now on. Now, what is going to come up next? What is coming up next is that, okay, so we are going to have a short lecture after this that's going to summarize whatever we have so far. Next up is going to be division. You remember from elementary school that division was a tougher cookie than multiplication, and it's going to be the same way in linear algebra also. Division is going to present us with more challenges and more work than what we have been doing. But fortunately, we have that little software that's going to help us take a bit of drudgery out of our shoulder, but be ready for a bit more work when we come to the case of division. Okay, until next lecture, good luck and God bless.